Hello and welcome everybody to the course Crystal Engineering, Chemistry Beyond the Molecule. Today we will have a look on the molecular aggregation of arenes. And then we will see that our formal scientists, chemists, observed some very interesting, amazing features of this molecular class. Have a look. Former scientists. While we speak about investigations in 1921, this is round about 100 years back. I would say with the first investigation about crystal properties, I mean cell constants, and molecular properties. And this investigation were done by Brack. What has he done? Have a look. Naphthalene, anthracene. And here are the cell constants. 1921, they were not able to determine the crystal structure, the molecular crystal structure, but it were possible to define the cell constants. What we see is the A-axis is nearly similar and the B-axis also roundabout. A little bit expanded, it makes sense because the molecule is a little bit enlarged. But the C-axis, have a look on the C-axis, this is a difference in the C-axis. And they said the reason must be, here, difference, must be on the dimension of benzene. And that's exactly what is absolute correct. If we look to the crystal structure of benzene, is exactly the roundabout, exactly with here the dimension, 2.5 roundabout. This is amazing. 30 years later, 1951, Robertson investigated really a lot of crystal structure of polynuclear aromatic hydrocarbons. And have a look what I have found. What he's found is that any molecule is surrounded by a maximum number of close neighbors. And the assumption is molecules assume equilibrium positions so that the potential energy of the system is minimized. Yes, and this is exactly what we assume in the case of close packing. What Robertson found, you can classify the polynuclear hydrocarbons in two groups. First group, molecular area small, for example naphthalene, anthracene, we have shown slide before. And the second group, molecular areas large, like coronine, shown here. This systematic study of Robertson was really great effort, because in this time, 1951, we need several weeks, months to measure and to solve one crystal structure. I think you know today you need only some minutes to get a crystal structure. It's really a huge effort. Well, have a look. First group, I said, molecular area small. And what he saw is, have a look on the ratio of the hydrogen and carbon. If you have a ratio Mn below 1.5, these are the small molecules, then you will find herringbone motif geometry angles. And I will show you a little bit later what it means. And the second group is if you look to the ratio, bigger than 2, when you will find a stacking motive, geometries, angles, round about 90 degree. Have a look here. Here, naphthalene, this is herringbone. Heringgräten in German. Herringbone, you see, is exactly what you will see in the fish. No? Herringbone. No? And you see it very nicely. The angle is here between two neighboring molecules here around about 40-50 degree. And if you look to carbon-rich molecules like chromium, then you have an angle around about 90 degrees. Okay. This was the first point. What does it mean? Naphthalene, anthracene, benzene. It means that the critical parameter for crystal packing is the stoichiometry of CH. Okay? And what I said it, close packing, structure based on efficient packing of objects. It does mean chemical nature of interacting atoms is not so important. Chemical nature of atoms or chemical nature of a molecule is not important. Much more important, interesting for crystal packing is numbers of electrons of contacting atoms are comparable. And if you look to the last two sentences, you can summarize and say molecules of a similar shape and size can take the same or similar crystal structure. This is really interesting. And much more, I think, for me, interesting too is that with observations of similarity is not restricted on hydrocarbons. Have a look here. A lot you will find in the database of crystal structure, a lot of iodine and bromine derivatives, the same substance, have exactly the same crystal structure. Have a look on this very, very simple compound. Iodobenzene, bromobenzene. Difference is only for substituents here. Have a look on the cell constants. A 15, 14, B 11, 11, C 8, 8, roundabout, yes. Same space group. Have a look on the crystal packing. You see here's the crystal packing of iodine, iodobenzene, and you see this exactly the same crystal structure, crystal packing, the case of bromobenzene. Same crystal structure. Or another example. If you change one chlorine substituent by a methyl group in a lot of crystal structure, not all, a lot of them. For example, there's a publication here from Desirajo, and he has shown that this is from 1986, and he has shown 100 pairs of molecules fits these rules. This is the same crystal structure. For example, this case, change one chlorine by methyl, same crystal structure. Change one chlorine by methyl, same crystal structure. And also here, always the same. The reason is that it's this is nearly the same spherical volume between chlorine and methyl. Both have a volume around about 20 angstrom cubic angstrom. Both cases. But one exception, one important exception, this rule fits only if you switch from one methyl to one chlorine. So if you change several methyls, so if you change both chlorines by methyl, you will not get the same crystal structure. Another example, dihydronaphthalene. and acridine, dihydronaphthalene and acridine crystallize isostructure. Same crystal structure. Once again, not the molecule is important, the interacting atoms and molecules is important, the electrons are important, and the similar shape. Here is the structure of dihydroanthracene and dihydroacridine. The difference is only with X, methylene group by amino group. This is exactly the same crystal packing, nearly exactly the same cell constants. So the geometrical factors are important with crystal packing. This is clear. And the shape of a molecular crystal is related to the repulsive potential field around. Yes? But, very important, what we have seen here, here's an aromatic system, here's an aromatic system, but not in this case. If you introduce one heteroatom in an aromatic system, when this introduction has an impact of electron distribution of the whole system, and now additionally to this close packing interactions or the features, where additional formation of anisotropic interactions possible. I will show you here. There's a very nice contribution, crystal growing design, acenes versus nitrogen heteroacenes. Effect of nitrogen substitution on the structural feature of crystals of polycyclic aromatic hydrocarbons. You see here a calculated electrostatic potential map of benzene and anthracene. And you see this is very, very similar. Yes? If you switch now one carbon atom of this aromatic systems by nitrogen, have a look here. This is the calculated electrostatic potential of acridine. And there's a great difference to these two compounds. What you see in the case of the acridine, that the importance of the CH contacts, typical for close packing, are diminished. And what you see now, additionally, CH-N interaction. And this leads to a new type of crystal packing. Well, coming to the end of this video of molecular aggregation of arenes. The driving force for any reference molecule is to be surrounded by a maximum number of near neighbor molecules. This is one key message, go home message. And the second, molecules of a similar shape and size can take the same or similar crystal structures.